All right, so I'm Sabyasachi Tiwari from Odin Institute for Computational Engineering and Sciences here at UT Austin. And today I'll be introducing you to EPWpy and MatCSSI and how you can do electron phonon physics using the software package EPWpy, which wraps another subpackage EPW on the MatCSSI infrastructure, which is developed in partnership with TSCC. So this is the outline of my talk. So I'll first introduce you to the electron phonon physics using EPW, and then I'll introduce you to programmable abstractions using EPWpy and how EPWpy helps in abstracting these calculations and creating workflows. Then I'll introduce you to the integrated MatCSSI portal, where you can actually run these codes and calculations. And eventually I will conclude. So electron phonon physics with EPW. So first, what exactly is the electron phonon physics? And before I go into that, let me tell you that EPW is actually a code that helps you perform various calculations for electron phonon physics. It's actually a big collaboration across 2 or 3 different continents, includes the US, our group, Roxana Margine, MatCSSI group, and Europe includes Mario Zacharias, Professor Ponce, Professor Caruso, and Yangu Son's group, and also my previous colleague John Bartolome. So a lot of things that I will be discussing today is actually the work done by many people who you see here as the list of developers. So what exactly is electron phonon physics? So if you think about a lattice or a material uh, at a finite temperature, the material in general is not still, so atoms are not still, rather they are always vibrating. When you inject a carrier into this material, it could be through photon excitation, it could be through an electronic excitation where you put basically gates around and use an electric field. This carrier gets into the material and basically interacts with these vibrating atoms. These lattice vibrations can be quantized in terms of quantum mechanics, and these quantized lattice vibrations are called phonons. And the interaction between this carrier and these phonons is what we call as the electron-phonon interaction or electron-phonon coupling. So electron-phonon coupling is basically interaction between the electrons or these excited particles with the vibrations of the lattice, quantized vibrations of the lattice. Now, where does really electron phonon physics play a role, and where do we actually see its implication in our practical life? So, all of you must have used electronics, computers, cell phones, and these electronic components are actually made by very small electronic devices called transistors. So, if you take a microscope, open this thing, and look inside, you will see chips like these. Now, all of you must have experienced that with higher usage, so if you use it more, your devices heat up, and as they heat up, they actually become slow. This is actually manifestation, or one of the manifestations of the electron phonon physics in practical life, because what happens is here we see an experiment of electronic mobility, which basically measures how fast the carriers are moving in a material as a function of temperature. And we see that the mobility decreases as the temperature increases. Lower the mobility means lower the speed of your devices that you are using. And this happens because of the phonons. As temperature increases, phonons start scattering more. Now you think, okay, that's a finite temperature effect. What happens at 0 Kelvin or close to 0 Kelvin? So very low temperature. So you must have seen these machines, which we call MRI machines, and they require to use a very high magnetic field. And in general, superconductors are used to generate these magnetic field. And what superconductivity is that at a very low temperature, we see a sudden drop in the electrical resistance of certain materials. Here we see niobium tin. And basically, the superconductivity's origin is due to the electron-phonon interaction. So creation of Cooper pairs, which are basically appear because of the electron-phonon interaction. Now, there are other practical avenues such as light matter interaction. So here what we are showing is a solar farm which is using silicon photovoltaics, which absorbs sunlight and convert it into electricity. And silicon is actually an indirect bandgap material. So what happens is that in indirect bandgap material, the light cannot be directly absorbed. Rather, it requires phonons to be able to absorb the sunlight and convert to electricity. And in the visible range of silicon, this absorption of light is facilitated by the phonons. So what I'm trying to say, the take-home message in here is that the electron phonon physics actually impacts all many walks of life and many practical applications. So where does two phonons come from, and where does this what is the simple way of understanding this electron phonon physics mathematically? So you can take a material, for example, here we have diamond, and we can look at the band structure of the material. And then we can basically move the atoms along a phonon mode or a vibrational mode of the material. And what we see is that there is a change in the band structure. Now, this change can be traced back to simple Cornsham equations, where for here on top you see the single particle equation where the first part is the kinetic energy, the second part is the potential energy, where we have the self-consistent field potential. And this equation is actually solved self-consistently with density in order to obtain the energy minima. Now, if you look at this self-consistent loop, we basically obtain the density from the wave functions, and this potential actually carries this electronic density. But also this potential, the self-consistent field potential has a part of the electron-ion interaction, where tau k represents the position of the atoms. And this equation is solved self-consistently to obtain the self-consistent field potential and the density. But what we actually see here is that the self-consistent field potential depends on the atomic positions. So if I simply look at the self-consistent field potential, I can represent it as position of electrons and then the position of all the atoms in your crystal. And what phonons are generally vibrations around the equilibrium position. I can what we can do is that we can perturb this self-consistent field potential with a small displacement of the atoms. What we see from here, we can just simply do a Taylor expansion, and we obtain terms like this, where we have the self-consistent field potential at the equilibrium position, and then we have Taylor expanded derivatives of the self-consistent potential linear response. So temperature adds this perturbation, but even due to quantum mechanical effects, at 0 Kelvin, you still have this perturbation of the atomic positions. Now to visualize, if we look at the self-consistent field potential at the equilibrium position, it would look something like this, well periodic and well arranged, with a small displacement, which you can see here. The self-consistent field potential changes, and the perturbing potential is basically the difference between the self-consistent field potential with displacement and at equilibrium. And you can see here, this is how this perturbation looks. One thing to note here is that this perturbation is well localized, and this will become important at later slides. Now, there is using this perturbation in potential, we can actually calculate many things. So we can calculate the perturbation to energy, we can calculate the perturbation to wave function, and we can also calculate stuff like the transition rates. The calculation of this perturbation potential coming from the atomic vibration is key to calculating many properties. For example, the perturbation to energy is basically used for, you can be used to calculate the band renormalization. So band structure change that I showed earlier um, is basically the change in energy due to this perturbing potential. Change in the wave function can be used to actually calculate optical transition or optical absorption uh, due to phonons. And these transition rates can be used to calculate the transport coefficients such as mobility. So in a nutshell, calculation of this perturbation potential is key to calculating many of these practical properties. Now, if we look at so how do we really calculate this perturbing potential ab initio? So if we look at this derivative of self-consistent field with atomic displacement, uh, here these displacements are basically in a supercell. So if you take a material, what these kappa alpha p represent is the kappa represents the atomic position, p represents the supercell, and alpha represents the polarization or direction of the movement of atoms. What we do is that we convert this supercell quantity into a unit cell quantity with the lattice periodic part and represent it in terms of reciprocal vectors. And this is what gives us what we call as the electron phonon coupling, G. And this lattice periodic part can be obtained very simply from the derivative of the self-consistent potential using what we call DFPT. This is how the expression looks, and it carries multiple ingredients. So first, it has the incommensurate modulation, which is coming from the supercell. We have the 0-point amplitude, the phonon polarization vector, and the potential variation from the ion displacement itself. And all these ingredients are actually can be obtained using density functional perturbation theory. Now, if we look at so if we can obtain these ingredients using the density functional perturbation theory, uh, then the problem is kind of solved. The problem is that if we look at the electron phonon coupling, uh, we need to obtain it for again the Q grids, or what we call it, the wave vectors. And we need to obtain it for a denser grid. And the way you can think about it is in terms of sampling, is that think, for example, if you have a quantity that you want to actually discretize. So here we take an example of the energy bands. And here we are looking at a cut in the energy band across the two wave vector directions. And if we actually look at that, this white line represents the energy band, which we need to actually approximate. But if we just have 4 grids, we will only be able to obtain a small part of this energy band structure. So to obtain the full energy band structure correctly, or all the energy values very correctly, what we actually require is a very fine sampling of the Brillouin zone. And the very fine sampling required here is actually necessary to obtain any kind of physical properties. So generally, in these kind of calculations of physical properties, we need to converge these quantities, and the denser is always better. So in a nutshell, the dense K and Q grids are needed for calculating the observables. Now, if we look at this expression carries three things. First, it carries the wave functions, then it carries the derivative of the potential, and then and basically it also carries the polarization vectors. Now, if we look at the wave functions, those we obtain from non-self-consistent field DFT calculations. These are very cheap for unit cells, so they can be done for very dense grids. However, the displacements and derivatives of the self-consistent potential are obtained using DFPT, and those calculations are very costly. And these calculations cannot be performed for dense grids. And that's where what we do in EPW, and that's where EPW comes into picture, is that what we need is a reliable method of interpolating the electron phonon matrix element instead of calculating it for a very dense grid. So how we do that? For that, what we do is that we use the one-year functions. So basically, one-year functions are a representation, are localized orbitals, which look something like this. So they are localized around the atoms. and are a representation or a transformation to the plane wave functions. In the DFT or plane wave DFT, we basically obtain quantities using the plane wave function. Um, Using the one-year functions, basically, what we can do is that we can represent these plane waves into a localized representation. Now, what is the benefit of this? Is that first benefit is that in the localized representation, once you have obtained the localized representation, you can interpolate it to any k arbitrary k point by just performing an inverse Fourier transform. And this is what we call as the one-year functions. And basically, this inverse transformation is what we call as the one-year interpolation. So first step is to obtain the one-year functions. And then the next step is to interpolate these one-year function to an arbitrary wave vector. And these UKs, or what we call as the one-year unitary matrices, these are generally obtained in the interpolation step by just diagonalizing the one-year Hamiltonian. So now we have a reliable method of interpolating the wave functions. What we can do is that we can just directly uh, represent the electron phonon matrix element in the one-year representation. And that was done for the first time in 2007 by Professor Giustino in this work. And with that, what we obtain is basically a localized representation of the electron phonon matrix element in the one-year basis. So the process that and since we have now the localized representation of electron phonon matrix element, we can actually interpolate the electron phonon matrix element to any arbitrary k and the q point. So the process, what is followed generally, is that one obtains the electron phonon matrix element on a coarse grid using DFPT. Then we obtain the one-year representation of these electron phonon matrix elements. And from this one-year representation of electron phonon matrix elements, we can just Fourier transform them to obtain them on a fine KQ grids at any arbitrary KQ grid. So what this method uh, does is that it provides a reliable method of interpolating the electron phonon matrix element. So this is generally the procedure which is followed. As I said in the previous slide, we obtain the electron phonon matrix element on a coarse KQ grids. And this process is generally done with a combination of DFT and DFPT, so density functional theory and density functional perturbation theory, using quantum espresso. And then these quantities are imported inside EPW, where in the first step, we perform one-yearization of the electron phonon matrix elements and the related ingredients. And from this one-year representation, we obtain the electron phonon matrix elements in a fine KQ gray. So everything here in the red, the self-derivative of the self-consistent field potential, the displacements, um, and the wave functions are obtained from quantum espresso. What EPW does is the one-yearization and interpolation of these ingredients which are obtained on the coarse grid using DFT and DFPT. So using EPW, so EPW is a sub-package within the Quantum Espresso DFT package. So you can install EPW with Quantum Espresso. What EPW does is that it interpolates the electron phonon matrix elements obtained from DFPT. And once we have these interpolated quantities, we can actually perform various physical property observable calculations for very fine KQ grids and converge these calculations to obtain meaningful physical observable results. And these calculations, and so EPW can perform various calculations, including transport coefficients like mobility, polarons, formation energies, superconducting critical temperatures, temperature-dependent band gap, and optical absorption processes. And today, those of you who will stay for the hands-on, you will actually see how we calculate transport and polaron properties. Now, if we look at the current computational materials design landscape, today computational materials design impacts all walks of life. there are various calculations, there are various physical observables of practical importance, such as optical absorption, charge transport for logic devices, carrier dynamics in electronics, polaronic physics for oxides or memristive devices, superconductors. These are all can be reliably obtained using the EPW code. However, there are issues. For example, these calculations are require very complex workflows and require user intervention. As I mentioned, there are certain ingredients that we obtain from quantum espresso, and then we port them to EPW, and within EPW also there are various steps. So it really requires an informed user to be able to use these codes, to be able to use these methods efficiently. Uh, one major issue that has been around is the high throughput study of large material databases. The reason is that because these calculations require a lot of user intervention, it's challenging to perform many materials at a time. So in general, uh, in terms of practical calculations, what we figured out that the challenge is twofold. One is streamlining these calculations. The other challenge is actually analyzing the data in the real time, because since you need to figure out if your calculation is going correct or if there are errors before moving on to further levels of calculation. A typical workflow of EPW looks something like this. So generally we start with a material, we perform the self-consistent field calculation, we perform phonon calculation which require ingredients from SCF, and we perform non-self-consistent field calculations. And from the phonon calculation, we obtain the derivative of potential and the polarization vectors. From then non-self-consistent field calculation, we obtain the energy eigenvalues and the wave functions. And then we put them inside EPW to perform one-yearization. And and the one-yearization is performed using 1-year-90 in the library mode. And from this, we obtain the unitary transformation matrices and the ingredients in 1-year basis. And then finally, we perform EPW interpolation step to interpolate the electron phonon matrix element on a very fine KQ grid. At each of these, so you can see there are many steps. At each of these steps, you need to decide multiple parameters. For example, for a CF, you need to know wave function cutoff, pseudo potentials, bands. You need to determine how many bands you want to perform. In the NSCF calculation, you need to determine the density of your K grid. For phonons, you need to determine the density of your Q grids and many other inputs. And in the first step of EPW, you need to figure out what one-year functions you are going to use, and then you also need to check for correctness if your one-year representation is correct, or you need to tune it, enable to be able to obtain optimal one-year functions. And then again, finally, once these decisions have been made, you have finished the calculations up to the obtaining the electron phonon matrix element in one-year basis, you have to obtain you have to provide physical property related inputs, such as for if you want to do optical absorption, what would be the optical absorption range or the photon range that you want to give. Or for example, in the carrier mobility, you need to choose what Fermi surface thickness you are actually going to use. Now, there are more complicated workflows for EPW. For example, as we know, DFT underestimates the gap. So sometimes we want to correct the band gap using the GW quasi-particle energies. So in that case, we actually are able to import the eigenvalues to EPW. However, it adds to some level of complexity and many more decision choice you need to make. And now, in the newer versions of PPW, you can also calculate things such as the exciton phonon coupling. And these common workflows are even more complex with more points to make decisions and also more points to make errors. And if you look at the executables, in a typical EPW calculation, we deal with multiple executables, for example, pw.x, ph.x, So this first part is done in the quantum espresso. Then we have 1 year 90 for modernization. And then the second part is done in EPW. So in a typical EPW calculation, there are multiple codes which communicate with each other. There is quite a lot of data transfer and one requires user intervention. And is a need for unified method to streamline these calculations. And that's where comes the EPWpy. So in EPWpy, what we achieved is what we call as functional abstraction. So a material, basically in a typical EPWpy calculation, what we do is that we represent them as objects. And calculations are basically methods. And each of these calculations can be seen as functional block. And all these calculations basically have three steps. So the first step is to define the inputs. So for example, here in the SCF calculation, we are only defining the K points because many of these inputs are already defined automatically, which are kind of going to remain the same. And those inputs are defined here at the object level. So for example, in a calculation, you're not going to change the structure of material or the wave function cutoff or the pseudopotential. Those things can be just defined as the object, as the attributes of the object itself. These will be carried forward to the calculations, and we only need to define specific inputs in the calculation for that particular calculation which are needed. So redundancy is reduced. Within EPWpy, each of these calculation basically are three-step process. So first step is defining the inputs. The second step is preparation. So preparation basically means uh, copying or transferring the files which are required for the particular calculation. And then the final step is running the calculation in itself. After each calculation, what happens is that the object remembers what calculation was performed and what values were obtained. So these values basically become the attribute or so for example, here we did SCF. The object after this calculation will remember the SCF attributes or the inputs that were used. So if we are using a common calculation again, those values will be carried forward. Here, as I showed earlier, that in EPW calculation, you require the workflow is basically multiple calculation blocks that you need to put one after the other, and eventually you do a final calculation. Uh, Here in EPWpy, basically what you can do is that you can arrange these blocks one after the other, and depending on the position of the block, there is a connection that is built. So for example, if you performed a SCF calculation, and if you perform an SCF calculation afterwards, basically, a non-self-consistent field calculation requires inputs from the SCF, finished SCF calculation, for example, the charge density. Those are actually carried forward to the next calculation. So you do not have to do it by yourself. These data transfers are handled automatically. And as I said earlier, that after each finished calculation, you keep adding more and more attributes to your object. And basically, your object will remember what calculations were performed and what values it got. Now, what is the benefit of this? One big benefit is that we can actually arrange these blocks together in a method like this. So, for example, here I have arranged SCF and an SCF block together. And when they are arranged together like this, they can be thought of as a single unit or a single functional abstract block. So basically, what the way you can think of this entire procedure is that this SCF and SCF, eventually you are getting just one output. And these things have become kind of an abstract single executable function. And one of the benefits of being able to abstract these calculations and contain them into a single functional block is that now these functions or these methods can be actually encapsulated into single blocks, and we can use out of the box optimization algorithms even to optimize certain parameters, or there are many other ways of actually being able to perform various types of optimization calculations uh, once we have understanding that we can write these blocks as a single function. So here I give an example of this sort of an optimization where what we do is that we take a silicon unit cell. We perform the SCF and band structure calculations. So we basically write two blocks. And after the band structure calculation, one can obtain the effective mass. What we actually do here is that we define this effective mass as some sort of a loss function. And then this effective mass can actually be optimized with respect to the stress applied. And since this is just a function, this is the object, we can actually perform this calculation in a loop. And here we actually use differential evolution to figure out that what could be the optimal strain that would lead to the best effective mass or the lowest effective mass for the conduction band of silicon. So with this kind of abstraction, we can use out of the box optimizers. For example, here we use differential evolution in order to perform such calculations. Now, as I said, that you can arrange blocks, and these calculations are very thin in terms of inputs. What we can do is that we can represent an entire EPW calculation itself as kind of a functional block, which is encapsulated with the EPWpy script. And we can even optimize for certain parameters. And today you will actually, those who will stick up to the hands-on will see, and those who won't can look at the material, that how we are able to do perform tests like the convergence very efficiently with the EPWpy and these functional blocks. So here is what EPWpy in general is. So EPWpy is a Python package which helps you to perform such kind of object-oriented abstraction of calculations. In EPWpy, basically it currently interfaces with Berkeley GW, and there is also partial interface with VASP and Abinit. Basically, in EPWpy, all these calculations that I showed you and the workflows can be done very efficiently. And it also comes with other interfaces, and we'll use some of them. One interface it comes with is the materials project. So giving the materials ID directly, you can actually download the structure, and you can perform other calculations with the materials project interface. It also comes with an interface to pseudo-dojo. So pseudo-dojo is a repository where various pseudo potentials are kept. And basically, EPWpy, depending on the material, can download a particular pseudo potential from automatically from pseudo-dojo. So even that level of so it's automated up to that level. And then basically, the future plan with EPWpy is a complete interface with various DFT codes so that they can be worked with EPW. But currently, we only support Quantum Espresso for the full EPW calculation in EPWpy. So this is how a typical EPWpy based script looks like. So top is actually defining the material object. So here I have defined silicon. So you can see I directly download the structure from the materials project by giving the materials project ID of silicon. We can manipulate the lattice structure of silicon, the lattice constant. And here you can see that the pseudo auto is true. Basically, this is going to download the pseudo potential, norm-conserving pseudo potential for silicon directly from pseudo dojo. And once we have defined this material object, all these files, self-consistent field, non-self-consistent field, phonon, EPW will actually be generated uh, automatically. So you don't have to provide the redundant inputs at each of these calculation levels. So you can see Each of these calculations or methods are very thin in terms of the inputs. So for SCF, we just need to give the K points. For an SCF, we need to give bands and grades. And for phonon, we just give the Q grades. Also, just like quantum espresso, one has cards in the EPWpy. These cards basically become a dictionary. And there is a very strong documentation of EPWpy where you can just use Python help to obtain to understand what basically each of the dictionary attributes are. We will go through that as well. And here is what a typical EPWpy script looks. It's very thin in terms of inputs, and as you can see, within like 40 or 50 lines, we are able to perform a very complex EPW calculation. And there is not just EPW, we can even perform the GW calculations with the Berkeley GW interface inside EPWpy also very efficiently. So as you can see, this is performing a GW calculation of epsilon and sigma, and you see the inputs are very limited. The reason why we are able to keep the inputs very limited is because the information is transferred across various methods. And the other thing is that all the data transfer is handled internally. So the user can control the data transfer the way they want, but a larger chunk of the data transfer is just done automatically. So there is no overhead of user interference in determining the data transfer. And for EPWpy resources, so it's hard to cover everything about EPWpy and its all functionalities. The resource available is the EPWpy's website. In the EPWpy website, you can find the full code documentation, and you can also obtain tutorials. So there are, as I said earlier, that there are various properties that EPW can calculate. All those properties can actually so there are dedicated notebooks on the EPWpy website which calculate each of these properties, and they can be used very easily. And these notebooks, as I said earlier, can now be run on the TACC infrastructure. And this is what we call as the integrated MatCSSI portal. So the plan of the integrated MatCSSI portal is actually to enable ab initio material simulation environment and interoperable. So where one can use various codes such as ab init, quantum espresso, wasp, and basically this MatCSSI portal gives a single user interface to be able to use all these various codes. Also, it gives access to various compute infrastructure. For example, today we will be using the Vista supercomputer. Future, there will be Horizon, and one can also use supercomputer like Frontera. And eventual plan is to be able to also use Amazon Web Services as this project goes through. And basically, the idea here is that through a single user interface, we would be able to perform various material simulation calculations using various codes, and EPWpy would act as the main package manager. So MatCSSI is a portal which is powered by TACC. So I think all of you must have seen the portal by now. Some of you will actually get to perform the hands-on today, where what MatCSSI provides is Jupyter Notebook interface to be able to perform these MPI calculations and these large scale calculations. And some of you will be able to do that in hands-on. Unfortunately, we couldn't take everyone because we had limited number of supercomputing reservations. However, future we will plan to have more. And also in this portal, any independent person can actually ask for allocation of supercomputing hours. With that, MathCSSI is actually a big collaboration, and there are many people who are involved in this, such as Professor Giustino, Professor Stanzione from TSCC, uh, Dr. Metal Dahan, Professor Zenglu Lee, Professor Louis, and Professor Mark It's supported by NSF and is supported by the NSF award number 251830. With that, I conclude. So I showed you that electron phonon physics is important for calculating many practical properties. And EPW provide a convenient tool for exploring the electron phonon physics. These are the important, so this is the GitLab repositories where you can find the codes and also some wiki about them. So with that, I thank you.